Okay. Hi, everyone. Is the audio working? Yeah? All good. Okay, perfect. Well, thank you, Tesh. Thank you, Thomas, for the introduction. Thank you to the DataGeeks for having us. My name is Christian, and I'm going to talk a little bit about Iceberg today. We'll first do a small introduction on what a lakehouse actually is, maybe to just judge the audience here a little bit better. Who here knows what a lakehouse is? Okay, so quite a few. Who here know what Iceberg is? Okay, and who here is actively using it? Okay. We'll see. So, not all hands have been opened with the first question, so I hope my introduction of the lakehouse is good enough. We'll see. Yeah, so let's get going. First, quick introduction of myself. So my name is Christian. I live in Hamburg. I came down here for, well, this meetup mainly. I'm a software engineer first and foremost, so I develop Rust code. And what I currently spend most of my time on is Lakekeeper. I'll talk a little bit later again what Lakekeeper is, why you need a catalog in a lakehouse. Well, said in one word, Lakekeeper is a Rust native Apache license Iceberg REST catalog. Now, the folks who are using Iceberg probably know what it is now. The others maybe not. And I'm a contributor to Iceberg, mainly to Iceberg RS, so to the Rust side of things. Also a little bit to the core project, but mainly due to the REST specification. Okay, I want to start with an introduction. Not too lengthy and reasonably accurate history of data analytics systems. So let's get going. Why are we where we are today? So shortly after the Big Bang, we started to develop relational database systems, right? And we started to use them for data analytics use cases as well. So today, everything I'm saying is related to data analytical use cases, right? So processing large amounts of data about big tables, and not about updating a single row, not about what we call transactional systems, which is what you would typically need in application design. But I'm talking about analytical systems. So we already had these databases, so we started using them for, as a data warehouse to store data. And that was a really marvelous time, right? We had a few clients who worked with the data. We had a central data analytics team, and databases, they're asset compliant. They're transaction safe. You can read and write at the same time, and nothing breaks. We have a concept of a schema and schema evolution. We have governance and access controls all baked into the database. But then time went by, and our requirements changed a little bit. We no longer have a central data analytics team. We have people all over our company working with data, right? So everyone's working with data today. We have, AI use cases, robots, machine learning models. They all need data, and they need data in huge quantities. And that, brought our little database friend here into trouble, right? So what we started doing is we started to scale the database, right? We used bigger and bigger databases. We tried to parallelize them. But eventually we noticed that one of the core problems of databases and why they don't scale that well is that we have a single box, and the single box shares compute and storage. It's both in this one box. So we need to scale this one machine, which is our data warehouse, to be able to serve more data. And this is not what we want. Instead, we have all of these different compute systems up here, and they already have a CPU. So why don't we use this CPU power that we have up here and directly access the data which is stored on our storage? So in these traditional systems, compute has been a bottleneck. It doesn't scale well. Scaling a single machine is super expensive. And then also, I really like my image down here. Rest in peace, ODBC and JDBC. So we had these database protocols, right? They are serial. They are 30 years old, and approximately that's how fast they are. So they're super slow, which is absolutely fine for applications, right? For transactional systems. But this is using ODBC and JDBC is the worst you can do for a system that's supposed to ship a reasonable amount of data. So we needed something new. And what was the new thing that came around? Well, big companies started to develop in the Hadoop ecosystem, right? And in the end, we ended up calling this a data lake. So the core principle of a data lake is that we just get rid of this gatekeeper of a database compute, and instead we have all of our different applications directly access files on the storage. In order for us to be able to do this, data needs to be on the storage in an open format, right? Postgres also stores data somewhere, but in a format that is only known to this database. Instead, what we want to have is we want to store data in an open format on the storage. Imagine a CSV file, just much more performant. So data lakes, in contrast to what we had before with our database, data lakes are super scalable and very, very performant. So basically we are just using S3, we're putting on it all of our files, and that scales like hell. It also enables heterogeneous use cases, right? So we can use different engines, one engine for BI, one engine for ML, and so on, and they all access the same files on our storage. The problem is that unless you have a construct on top of that, a data lake doesn't have these properties that we have seen before in our database system. So by default, a lakehouse is not transactional safe. We have no clue of how the schema should look like, and we don't have any access controls. So why don't we take the principles of the data lake, like storing the data in an open format on an object store, and the principles of a database, and put them together. And then you end up with something like this. I call this the marketing slide because it looks so easy to do, and it's actually not that easy. It's a little bit harder. So the basic principle here is that, well, why can't we use an open storage format, for example S3, and then put a metadata layer on top of it, for example Apache Iceberg, and I'll come to that in a minute. And then we have all of we have the best of both worlds. We have all what we've known from a data warehouse, transaction safety, and so on, and we have everything from a data lake, especially scalable, performance, access to data. So this is the basic idea of the lakehouse, right? And this is why, in 2017, Netflix and other companies started to develop these metadata layers that enable database-like access on on object stores. Okay, so now this is what we want to have, basically, and like the rest of my talk, I'm going to talk about why this is actually so hard to achieve and how we can still do this. Because as simple as the slide before looks like, we just need this object store, and then we need this format that enables transaction-safe access, this metadata layer on top. And both of these are available, right? They're both open source. But it's still hard to build such a system. So why is that? So the overall goal of a lakehouse is that we have shared data and decentralized specialized computes, right? So different people want to work with different query engines on data. We might have some people using Python for ML. We might have other people using dashboards. We might have other people's data engineers using something like Spark. But what we originally did when we, started the journey of the data lake is, we had this monolith of a relational database system, and then we used Thor's hammer and we smashed it into pieces, and then we landed exactly on this journey that I just explained. And out fell all of these pieces here on the left. And in order to be able to collaborate with different compute engines on shared data, we need open standards for all of these different layers that we see down here. Because if we don't have open standards down here, then we can't switch and pick the compute engine that we would like to use. So we started to develop these layers, right? And we started with, we needed a physical storage. such as S3, as I said before, Azure Data Lake Store, Ceph for on-prem deployments, so S3-based deployments. And we pretty much agreed on that. So that's a check, that's set. Also, we need an open data format, right? We need to store data in some way on the lake that different query engines can understand. And, well, CSV is not a good file format. It's awfully slow. And it's not, type safe and so on. And so eventually Parquet was developed, and it's pretty much the standard today. Who here is using Parquet? Okay, all the others should Google it. It's really good. So it's a columnar, it's a super efficient way to store data in a file. Yeah, it's columnar, so it's perfect for analytical use cases. Down here, like with these two layers, we have a data lake. Like that's not enough for a lakehouse. We don't have transactions. Like if someone writes a file and another one reads a file at the same time, it's unspecified what happens. That's nothing to have in production. So we need something else. We need a table format. And this is where Iceberg comes in. So what is Iceberg? Well, Iceberg was developed at Netflix in 2017 by the people, actually, the New Weeks, Ryan Blue, who are still the PMC members of the Apache project. So they're no longer working at Netflix. They had quite a turbulent journey. They founded their own company, which was then acquired by DataGeeks for $2 billion. Crazy amounts of money flowing there. Yeah, so it was originally developed at Netflix to solve exactly this problem of transaction safety on data lakes. And it was donated to the Apache Foundation in 2018, and it has been an Apache project ever since. Iceberg is a high-performant table format for huge analytical tables, and it uses Parquet under the hood. So it's a metadata layer on top of Parquet. Well, basically, I copied this from the website. So it brings the reliability and simplicity of SQL tables to analytical data and to big data. And the project, like Apache Iceberg is not the only project in the space. I think there are 3 projects worth mentioning. There's Iceberg, there's Delta Lake, and there's Hudi. Hudi is very streaming oriented, which is why I'm not talking about it too much today. And well, Delta Lake and Iceberg are converging on a binary level. So Delta Lake was developed by Databricks. Now Databricks acknowledged that Iceberg is the way to go by spending $2 billion to buy the creators of Iceberg. And now they are working to make those files, or keeping these file formats compatible, and basically building a joint feature set. So Iceberg is the way to go, and you can also see this here on the right. So these are just an extract of some of the contributors of Iceberg. AWS has been in there from the beginning. Very much different to Azure and Google, who joined a little bit later. But they also joined. Yeah. Okay, so this is Iceberg. And Iceberg, so Iceberg is a table format. But a table format alone is not enough. Iceberg as a table format also needs a catalog. And this is what I want to talk about next. So, as part of the Iceberg project, there is a specification for the so-called REST specification, or IRC, Iceberg REST Catalog specification, which is basically an open API, specification that is part of the Iceberg repository, and that specifies how a catalog for Iceberg should work. As part of the Iceberg project, we don't have an official implementation of this catalog, right? So Iceberg just is a specification, and then we have different implementations out there who implement this standard. And we're one of them. So Lakekeeper is one possible implementation out there that implements this. Why do we need a catalog at all? Well, first of all, we need a single source of truth for table metadata. So an Iceberg table has at the top basically a table metadata, a JSON file which keeps track of all the different snapshots and all the different things that happen to this table. And we need a central place to store this data. We also need this central place to have a good old database built in, basically, because the catalog also takes care of multi-table transactions, right? If you have multiple tables on S3, it's really hard to have a transaction that spans multiple tables. And this is what we have the catalog for, which can do this. So yeah, there are a few more advantages on why we need this catalog. I guess sufficient to say today, this is a required component. If we build a lakehouse, we need a catalog. And like specifically for those of you, I mean, who are already using Iceberg might know this. Like this REST specification wasn't the first attempt of Iceberg to build a catalog. We've had other catalogs in the past. I listed a few down here. All of them are legacy. Hadoop, Hive, Glue, JDBC, Dynamo, ECS, Nessie, there are more. There was a huge mess in the catalog ecosystem, and this is all consolidated now around the Iceberg REST specification. Maybe to just pick out Glue, like the name in the community is a little bit like mixed. So of course Glue itself is not legacy, and Glue today even speaks the Iceberg REST catalog language, so it implements the protocol. But there's also like a legacy Glue catalog, which still uses the old Glue APIs around Hive. So this is the catalog, and we need it. And then there are 2 layers left. And I want to talk now the last 10 minutes basically about these 2 different layers. Because this is where most implementations and where most people like stop thinking about this, right? You have everything that you need, right? Well, not quite, because when we smashed Thor's hammer into the database, we also got 2 pieces out, namely permission management, right? Every database is able to manage permissions, and also identity and users. We need a concept to share identity, to share users between compute engines. Because if we can't share identity, if we don't know who someone is, we don't even need to start with permissions, because identity is a prerequisite to have a permission management system. Okay, so what's the goal that we want to achieve? Well, we have 2 different users, like that's me and that's weird me somewhere in Denmark. And we want, what we want to achieve is that we have different users collaborate with any query engine they like on shared storage with secure data. So we have 2 different users. A user might use, once they might use Python, after that they might use, Trino, a shared query engine, and they both want to access a table, for example, a revenue table, with their personal permissions that are shared between these different query engines. And because a lakehouse is no monolith, this is actually surprisingly hard to achieve. But it's possible today with open source tools, and that's what my demo is going to be about. So the first question is, where should we store our permissions then? So we have this stack, and there are a few different places where you sometimes see permissions being stored. The first place is a query engine, right? Or a compute. And that's, of course, a very bad place to store permission if you want to use multiple computes on your data. It shouldn't be in your query engine. So it's not shared, so don't store it there. Also, we don't want to secure our physical storage. I'm happy to discuss that in the break. That's also not very nice, so don't just have S3 policy securing your data. There is a saying that goes, secure your data, not your storage, and there are many good reasons for it. So we have 2 places kind of left. So the first place is we can store it in the catalog or in a dedicated system that is only there for permissions. This is what I'm going to look at now. So how does this look like if we have permissions in a dedicated system? Just to make this slightly more concrete, what this could look like. So permission systems today, there are multiple tools out there that allow people to store permissions in different forms. There is, for example, Open Policy Agent. There is OpenFGA. Those are both CNCF projects. There are other systems out there as well, and they're super specialized in making permissions as flexible and as bulletproof as possible. So why don't we have, like, when we have such a system and then we have different compute engines and we can connect those compute engines to our catalog, then we can have some compute engines that, you know, might not be able to connect to this permission system directly. They're just connecting to our catalog, which enforces the permissions. And we can have other compute engines who can directly leverage the permissions in these external systems. So when we build something like that, as I said before, I don't want to talk about identity too much today, but it's super important that we also share identity in data systems. And this is something that has been a shortcoming for years now, but it's super important. Like, my theory is that data engineers are, you know, they want to make progress, and of course it's super comfortable to generate an API key somewhere and use it in your daily load, but it's super insecure. It doesn't come from your IDP typically. So I put that down here. So every system that creates a personal access token, client credentials, or passwords that is not your identity provider is another identity provider in your system and a security risk. Throw it out. So generate credentials in your IDP and nowhere else. So now we've talked about where permissions should be stored. But how can we actually enforce them? I mean, it's nice that we write them down, right? But if nobody actually enforces our permissions, we have a problem. So let's enforce our permissions. The first place where we can enforce permissions is in the catalog itself. So luckily, as part of the Iceberg REST specification, we have a concept called valid credentials. And it works roughly like this. So we have a compute engine. Apache Spark is just an example. It could be really anything. And this compute engine is running a query against an Iceberg REST catalog, for example, against Lakekeeper. Then Lakekeeper checks and validates the permissions and returns temporary credentials to Spark. And with these temporary credentials, Spark can now access the object store, for example, S3, and load some data. This is what is called vended credentials. There is another security mechanism as well, which is called remote signing. With Lakekeeper, we support both. And what both of these methods grant you is table-level security. So basically, you get storage credentials that are allowed to access the location of your table on S3. Because of that, you can use it for any query engine out there. The second way to enforce permissions is that the compute enforces the permission, right? So this could look something like this. This is the most complex slide in my presentation, I promise. After that, it's going to be much, much easier. So how this could look like is the following. So for example, we have a multi-user query engine such as Trino. And then we have a user, and that user logs into the query engine. And of course, because we're using OAuth and a proper authentication system, we actually log in using our identity provider. For example, AWS Cognito, Keycloak, whatever we are using. Then we are querying some data, right? And what happens next is that Trino contacts Lakekeeper and asks for data of a table. We validate the token from Trino, and we also validate the access, which is pretty much always going to be okay, because Trino is accessing the catalog with a system user. There are also other ways to do this, but for the sake of this example, we use that. Lakekeeper then returns the metadata for the table and storage credentials, so that Trino can access the storage location. After that, Trino goes to the permission system itself and checks the permission for Christian, right? And after that, Trino filters out all the data that I'm not allowed to see. So after that, it retrieves the data and returns the result. So these are two different ways on how security can be enforced. So we have, on one side, we have catalog enforced security, and on the other side, query engine enforced security. Catalog enforced security, the vendor credentials that I've shown first, it enables table-level security, right? And it doesn't rely on any filtering of the client, so it works with any client out there. So if I install you know, a Jupyter notebook and some Python on my local machine, I can use the security mechanism to get access to the tables that I, well, am allowed to see. On the other hand, if I trust the query engine to filter out results, I need to trust the query engine. So this only works if the query engine is maintained by administrators in my company. Because, I mean, we can easily see that here, if the query engine doesn't filter the data, if there's nothing forcing the query engine to actually filter the data, I just get back everything, right? So I need to trust the query engine to filter the data. Okay, so there are other ways which are, well, not very common today and not implemented. They still need some time. I'm not going to talk about those today. So, almost done. So collaboration on data, as I said before, is hard. So now we have filled up our stack here finally completely. And these last two layers, permission management across engines and identity across engines, is something that has been missing for a long time in the data ecosystem, right? And especially in open source tools. A solid governance on data has been the main reason, you know, to buy into a vendor solution. In a vendor solution, in a big platform approach that comes with these built in. And like my core message today is that that the open source world is ready and that everything that we need is out there to build open data systems, including permission management and identity. And I have a little demo. It just takes 2 minutes, not going to be too long. It's also going to be very unspectacular, but I still want to show this. Because it's actually quite hard to achieve. So let me go here, and that didn't work. One second. Okay, here we go. So, okay, I need to do that. Okay, so what we have now here is we have.
We lost him. Was there a second and then going back to.
Okay, then I'm just going to do this. And now I hope it's working fine. Yeah, here we go. So we have a setup now with multiple query engines. We have a Trino and we have a Iceberg, and we have 2 different users. I've set up a catalog in Trino before, so I have already created the connection from Trino to Lakekeeper. Everything you see here is also available as a Docker compose in our GitHub, and you can get this later. Now, I'm running a query as one user, and that user is called Peter. And, Trino, because Trino is secured by OAuth 2 properly, as you should do it, Trino asks us to log into our IDP. So I'm logging in here into Keycloak. And I can actually talk while typing, and this is much louder. Okay, let me use this one instead. So I'm logging in here now as Peter. The password is Iceberg, and it's not secret. And now I'm logged in. And as this user, I'm now creating a table that I call finance revenue. And I'm inserting some values, right? And also a table called finance products. And now if I open my catalog, let's log into Lakekeeper here. We have a warehouse. This is an Iceberg warehouse. And in this warehouse, we have, a namespace called finance. And in here, we have our 2 different tables that we can see here. Now, if I use a second user, like this is now Firefox, a different browser, this is a second user, Anna, we will see if I run this query here and log in as a second user. Here we go. Let's log in as Anna. Password is also Iceberg. And that we get a permission denied error down here. So this did not work, Trino user error. And we can also see that when we log into Lakekeeper, that we don't have any permissions assigned yet. So let's grant some permissions. So I'm entering the revenue table, and I'm going to grant some permissions to Anna. Whoa, to N. Okay, there we go. Let's just grant ownership here. We go back to Anna. we check the status. Now we can log in. We can see, we can now navigate to this space just by this one permissions because it's via, well, it's inherited basically. And in here we can see the table and only the revenue table, right? Why should we see the product table? We didn't grant permissions on it. And now we can also, well, if we repeat the query, very like unsurprisingly, it now works. Or it should work, except that I'm querying the products table, which I don't have access to. So revenue instead. Here we go. And I need to put this into a separate cell, then I don't need to log in every time. But here we have the result. And now the interesting bit is actually, I mean, now we have like permissions in Trino, right? But we can use the exact same permissions here, for example, in Jupyter Notebook, where I use Iceberg, a completely different query engine. And I can log in. I'm logging in. Here we go. And, well, this shouldn't work now. Let's see. Because I'm querying the products table, but if I query the revenue table, it would work, right? So we have two different query engines, and they share the permissions. The permissions are not stored directly in Lakekeeper. We just use Lakekeeper to manage them visually. They are stored in an external system, and we can share permissions across different query engines. Isn't that great? Like that's something you would expect, right? But it's super hard to achieve in an open ecosystem, right? Where it's well, which is a little bit fragmented. So what's Lakekeeper? Just this one slide, and then I'm pretty much done. So Lakekeeper is an Iceberg REST catalog implementation. As you've just seen, it's completely open source. It's Apache licensed, and it's secure out of the box, right? So we come with OAuth, we come with permissions. That's something that not everybody does, especially not in the open source space. And it's expansive, it's extendable with, I mean, it's Rust. We have a lot of Rust traits that you can use. Because it's Rust, you know, it's a small binary. It's like 70 megabytes. We have it in a Google distroless Docker image, right, with nothing installed at all, not even a shell, and it still runs. So it's super secure, it's minimal. We have a very good Kubernetes integration for those of you who need this, including multi-IDP support. So in addition to your regular IDP that supports, you know, OIDC or OAuth, you can also have Kubernetes workloads authenticate natively against Lakekeeper. That's something to discuss in the break. Is this the last migration? We'll see. Yeah, and that's it from my side. So everything that you've seen in the demo is completely open source. It's 3 commands to get it running: git clone, cd, and docker compose up. You'll manage that. And then you have a UI, and you can work with that. And in that demo, we have one identity provider, one source of truth for permissions, different computes, and some of them are shared. And the shared part is actually very hard to get right. And everything is 100% open source. And that's it from my side.
Awesome. Thank you so much, Christian. It was a really interesting talk. I guess we learned a lot about Iceberg, if you haven't heard about it today, and also about the permission issues that you might come across. So are there a couple of questions? I think we have a few minutes so we can take some. Okay, let me make sure there was a second microphone somewhere.
I can also use that one.
Yeah, you use that one and I distribute the mics.
Okay.
So I saw first hand up over there. Please raise again. I forgot what it was.
Yeah. You need to put it close to
Yeah, hi. I have a question about the permissions. You said you need to have an external system for that. What kind of requirements are for that?
What kind of requirements we have
Or
to...
where you want to store the permissions?
So, I mean, so we currently store them in OpenFGA, which is as our main storage, which is a relationship-based relationship-based access control mechanism. It's a superset of attribute-based and role-based access control. It's super fancy. So this is what we use, but again, like Lakekeeper is generic over the system. So we can support other systems as well, and we're especially looking into supporting OpenFGA as well, OPA as well. OPA, so-called Open Policy Agent, is a project that I mean, I think everyone here who works with Kubernetes probably knows it, because that's what it's like, where they have very strong origins. But it's a system where you can define policies in their own like policy language called Rego, and then you can define like who has access to which tables, right? So this is supporting. We already expose our permissions, even if they are stored in like OpenFGA or in any other system. We already expose them as Open Policy Agent policies, which is how we can connect Trino, for example, to them. But we can also support other systems in the future. So
communicate directly with EIM, like for example,
with IAM. So we do have very good integration, like with Athena, for example. It's also on our website, but not IAM specifically. The reason for that is that if you have like a token and want to validate, so AWS, if you use AWS Cognito, for example, for identity management, that we can integrate with very well, and that's also on our website. And the reason for that is that Cognito is OAuth 2. The rest of AWS uses a sign-in mechanism that is called SigV4. And this is a validation that you can only like make inside the AWS platform, which would like remove some of our like use cases which are cross-cloud. So we integrate very well with AWS, but not specifically with IAM. Yeah.
Awesome, thank you. There are a couple of more questions over there. So logistically, I'll give you the first mic, and then just
Yeah, thank you. Thank you for great talk. I have a question. Basically, I want to understand a little bit more how you managed to do that. Like, as I understand it, you managed to offset, preserve performance advantages of Lake storage by putting all the heavy lifting into the separate, scalable, and parallel access right enforcement modules, this Trino, for example, right? And I understand how to parallel the stuff if we are talking about accessing the data, because filtering could be done like in parallel without cross interaction between these separate modules. But what you have to do to enforce proper data integrity and access rights when the user wants to write things?
Yeah, so the way how Iceberg does that is actually, so the question is, how can we make sure, maybe rephrasing it a little bit, how can we make sure to not break a table while someone writes? And the answer is, Iceberg only ever adds files to a table. So let's say I want to delete a row, then I add a file. And in that file, I either write, I delete that row, or I rewrite, I previously had a file which had rows from like 0 to 100. I want to delete row 50, so just take this file, remove row 50, rewrite this file. And I call this a new snapshot, right? And this is how, and then, so Iceberg is based on a principle that is called optimistic write. So everyone who wants to write data just does it, You write out new rows, you might write out these delete files, and then when you're done writing, then you tell the catalog, okay, now I'm done writing, please accept those. And then the catalog will check if everything's all right. And if everything's all right, the catalog will accept that change. And otherwise, it will reject it. And this way, if we have multiple people writing, not all of them will get their way, of course. But there are like smart retry mechanisms and server-side deconflicting to make it reasonably sufficient. So it's guaranteed to never break. But of course, not everyone might come through if there are conflicting commits onto the same table. If you have, multiple people and they're all just appending files, appending data to the table, you can have arbitrarily many in parallel, and it won't break things. So I hope that explains it. Okay.
First of all, thanks a lot. Very good talk. I have a more elaborate question. So it's good to have a catalog, right, for the data lake and to find the data. What we see now is in the industry more and more that we also use the metadata to activate that. Some call it the data fabric and others. to use AI agents and so on, maybe building knowledge graphs on the metadata to better manage the data in the databases. So is like Lakekeeper, the intent of Lakekeeper to also become such agentic metadata layer so that you can then automate and augment your entire data ecosystem, or where is the boundary? Where do you stop, or when where are additional tools needed?
Yeah, so that's actually a very good question, and the answer is absolutely yes. So we are becoming this layer, and actually, like today, I lay more focus on what is Iceberg, but the category where we see us in is actionable metadata. So to give you some examples how we realize this. So first of all, of course, MCP is coming soon. Secondly, we already emit change events today. So every single thing that changes in your data lake, you can get a notification out of the system. So for example, you can notify, we support currently Kafka and NUTS, maybe more in the future, but we can emit those change events in the future. And we're going even one step further, and this is not going to be part of like the open source version, but this is like a plus feature that we add. Already, like Lakekeeper has an interface that is called, that is a contract verification interface. So we have multiple hooks in different places. And in the future, we will be able to stop a transaction from going through if it would break pipelines that depend on a certain property of a table. So for example, you have a pipeline, that pipeline depends on the customer having a column ID, and that ID column is lowercase. And if someone now renames that to ID uppercase or identity or whatever, we would stop this transaction. This is not there to prohibit innovation, right? There are many operations on a table that are non-destructive. You can always add a column, right? But you should not make certain type changes, and you should not rename a column. So we have also this interface where we, can control the way how different systems work with each other and advocate it. So yes, we have so much valuable metadata in there, and we need to get it out. Right now, we are already getting it out, and in the future, we are making it much more usable.
Nice, thank you. So we are a bit short on time today because we need to leave the building at 9. So I would suggest if you have further questions, go to Christian and ask him in the bio break. But thank you so much. I think this was also a really good question and answer session. So give another round of applause for Christian, please.